The remaining material for this week is all going to come from chapter 5 in your book, which is called Further Applications of Newton's Laws. So they're not going away. In this chapter, we're going to talk about friction, drag, and elasticity. Oh, well, here's an example of a lot of drag and a lot of friction for sure. We've got these Indy cars here, and there's friction between the tire and the road. And you also have drag, the aerodynamic drag that these cars are experiencing as they're moving around the track. And these cars are designed specifically to reduce the drag so that these things can move as fast as possible. What is friction? You all have experienced friction, of course. Friction comes in many different sources. Friction comes from microscopic imperfections in material surfaces, which cause them to interlock. Okay, so this is a very detailed zoom in microscopic version of what's happening. So you have this, this crate here on a surface. What if we want to slide this crate across the surface? Well, the surface we're sliding it across is not perfectly smooth. The surface of the crate is not perfectly smooth. There's going to be these little jagged edges. Things get caught on these jagged edges, and that's what contributes to the friction. When you rub your hands together, you're experiencing friction. Materials are rubbing past each other. They're not perfectly smooth, and when you do that, you can generate a lot of energy too. If you polish these surfaces, that helps to remove these imperfections on the surfaces, and then you get closer and closer and closer to a frictionless problem. Friction, an important thing to keep in mind here is for the problems we are going to solve, is that friction opposes motion. So whatever direction you're moving an object in, the friction or the drag is acting in the opposite direction. If something is going to, if an object is sitting still, friction makes it harder to get that object moving in the first place. If something is moving, friction will bring it to a stop if you stop pushing it or stop pulling it. But we're going to talk about two types of friction: static friction and kinetic friction. Now, the greater the normal force, the greater the friction. So we learned about the normal force. The normal force is the force that a surface is pushing back up on an object with. Okay, if you are on a perfectly flat surface, that normal force is just the mass times gravity of the object. If you're on an inclined surface, that normal force is going to be reduced because you are no longer on the perfectly flat surface. You've got some component of the acceleration due to gravity in the x direction and in the y direction, perpendicular and parallel to this new plane, and that's going to reduce the normal force between your object and the surface if that surface is tilted. Okay, so static friction is the frictional force that opposes the movement of a body at rest. So that's the static part. It's the friction that opposes the body at rest. As long as the object isn't moving, then the static friction force is always going to be equal but opposite of the applied force. So that static force increases, 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 increases to match the applied force until that applied force exceeds the coefficient of static friction times the normal force. The coefficient of static friction, this little mu, lowercase letter, Greek letter mu, sub s, is the coefficient of static friction. These coefficients are determined for every material. It's a property of the material. It essentially says how easy is it for materials to slide past each other. A smaller coefficient of friction means that there's less friction in the system. A larger coefficient of friction means that that object is going to be really rough. It's going to have a lot of friction associated with it. Now, kinetic friction is the frictional force that opposes bodies in motion. The coefficient of kinetic friction is always going to be less, almost always going to be less than the coefficient of static friction. And the kinetic friction force is equal to the coefficient of kinetic friction times the normal force. static friction is always going to be greater than the kinetic friction. Okay, if the coefficient of static friction is almost always greater than the kinetic friction too. So the static friction is always greater than the kinetic friction. This is a table of coefficients of friction. Your textbook has a table too. The values of these coefficients of friction depend on the nature of the surfaces, and these values are usually between 0 and 1. So let's see. The coefficient of friction for wood on wood. You're sliding a block of wood across a piece of wood. The coefficient of static friction is 0.5. The coefficient of kinetic friction is 0.3. Okay, so this larger coefficient of static friction tells us that it's going to be harder to get that object to move. There's going to be a larger force opposing you trying to get that object to move in the first place, but once you get it moving, you've broken the bonds, or you've broken the sort of interlaced rough particles against each of the objects there. You've broken those connections apart, and then you can start sliding the object a little bit easier across. So you have a reduced friction force that's opposing you once you start getting an object moving. I'm going to start applying a force very, very slowly on the trash can. And as I do that, that whole time I'm doing it before the trash can starts moving, my applied force is equal to the static friction force. Eventually, I reach an applied force that matches the maximum static friction force, which is the coefficient of static friction times the normal force. Once my applied force reaches the maximum static force or achieves or passes it, then the object will start moving. Then we enter the kinetic segment of that object's motion. Okay, and once we do that, we know the force of kinetic friction is less than the force of static friction. So once you've broken those sort of interlacing bonds between the surfaces, it's easier to get that object to keep on moving it because the coefficient of kinetic friction is less. That means the kinetic friction force is less. Once I've overcome that initial maximum static friction force, then it's just easier to push that trash can along, okay? And then I can reduce the amount of force that I'm applying just to continue keeping it moving here. And then the force of kinetic friction is always going to equal your coefficient of friction times your normal force. So once you've broken that static friction bond, you can actually start applying a little bit less of a force in order to keep your object moving forward. With that information in mind, I'm going to ask you about this question here. We've got a box on a rough surface, and it's pulled by a horizontal rope with tension T. Okay, the box is not moving. In this situation, what is the force of static friction? Okay, you've got 5 options here, and so just thinking about what we just talked about, I want you to answer what you think this question is. A box on a rough surface pulled by a horizontal rope with tension T here. Is the static friction force greater than the tension? Is the static friction force equal to the tension? Is the static friction force less than the tension? Is the static friction force equal to the coefficient of static friction times the normal force? Or is it 0? So remember, the box is not moving, but I'm pulling on it with some tension T. Before I move on to the next problems, let's talk about what the free body diagram would look like for an object on an inclined plane with friction. Here we have a car parked on a hill, which is the correct free body diagram. So it's on an incline here. Well, we know that the car is going to experience a normal force from the surface on the tires. So we've got to have a normal force pointing upward, so that eliminates E over here. We know that it's going to have a component, or it has weight, and so that that vector that represents the weight of the car must be pointing straight down towards the earth. The only 3 where the weight is pointing straight down, the weight vector is the first 3 here. And then we have the friction force, the friction between the tires and the surface. That's what's keeping our tire from our car from rolling down the incline. Remember, the car wants to move down the incline in this direction. So the force of static friction that's keeping it in place wants to oppose that motion. So the force of static friction needs to be up and parallel to the incline. And so the free body diagram for this car right here is going to be this middle one right here, C. We've got the normal force perpendicular to the surface, the weight of the object straight down, and the static force opposing the direction that it wants to go along the incline. We're going to use that same free body diagram in order to solve this problem here, where we've got a block on a ramp and there's a coefficient of friction between the block and the ramp.
We have a block with a mass of 2.5 kilograms on a ramp. There's a coefficient of static friction of this ramp, so this problem is going to involve friction. The coefficient of static friction between the block and the ramp is 0.35. We want to find what is the maximum angle this ramp can make with the horizontal before our block starts to slide down the incline. So we're going to keep on increasing the incline of this plane here. We're eventually going to reach an angle just where if we just bump over it just a little tiny bit, then this block is going to start sliding down the ramp, okay? So when the object is stationary, it has static friction. And when the object starts moving, then we start to think about kinetic friction. And so we, in order to find this angle theta here, are going to have to use Newton's second law here. And the first thing, though, that we're going to do is draw the free body diagram on the block. So we have our block here. We've got the normal force perpendicular to the surface. We've got the weight of the object, its mass times gravity, pointing downward. Okay, and then we have static friction. Remember that friction is always opposite the direction of motion. The forces of friction are always opposite the direction of motion. So this block is going to want to slide down the plane. So that means the force of static friction is going to be pointing up the plane. And I'm going to write it as little f sub s. So the pink here, that's the free body diagram for my block on the inclined plane. So then if I come over here, this angle here is theta. Then we already talked in a previous problem about how if this angle down here is theta, then this angle up here is theta, okay? And we already also talked about how we can find the x and y component of the weight here. So this makes a little right angle triangle where the weight is the hypotenuse here of this triangle, our weight vector. And then, so the opposite side from the angle, that weight component is going to be mg sine theta. And over here, the adjacent side to this angle here, that weight component is going to be mg cosine theta. Okay, so now we can solve Newton's second law for this problem. I'm trying to pick which color I want. Here we go. Well, let's start with the sum of all of our forces in the x direction must equal the mass times acceleration down the ramp. If I say that y is perpendicular to the ramp and x is down the ramp, okay? But we're not going to accelerate yet. We're going to find the angle just before our object starts accelerating down the ramp. So right now, our acceleration is 0, okay? And then our forces in the x direction, we've got the static friction force acting opposite the direction of motion. That's going to get a minus sign, so minus the force of static friction. And then the component of my weight that's down the plane, that's positive actually, it's down the plane here. That's going to be mg sine theta equals 0. So recall that the force of static friction is always less than or equal to the coefficient of static friction times the normal force. So as you begin to tug and tug and tug on this on this object right here, the coefficient of static friction is always going to equal the force applied until you pull it hard enough such that you can actually overcome that force of static friction and get the object to start moving. Okay, so the force of static friction is always going to be less than or equal to our coefficient of static friction times the normal force. And so just until you get it to move, then that force of static friction will equal the applied force. Okay, but we're thinking about just at the very moment when our object starts to slide down. So we're going to say that we're looking for that very moment when the force of static friction just equals our coefficient of static friction times the normal force. When this condition is satisfied, then after we reach that angle, then the object is going to start sliding down the plane. So that's what we're trying to find, this maximum angle we can go until we start sliding down the plane. So we're going to use, for the force of static friction, we're going to use the coefficient of static friction times the normal force plus mg sine theta equals 0. So we're trying to solve for this angle theta here, okay? But we know the weight, we know the coefficient of static friction, we don't yet know the normal force. So to get the normal force, we're going to need to come over here and look at this Newton's second law for the y component. We're also not accelerating in the y direction, so this part of the equation is equal 0. So the sum of all my forces in the y direction, we've got the normal force perpendicular to the surface, so we've got the normal force, and then we've got, acting in this y direction, we've got minus mg cosine theta, that component of the weight, perpendicular to the plane. So that's minus mg cosine theta. So this tells us that our normal force is equal to mg cosine theta. So I can take this normal force and stick it in this equation right here. So then I have minus the coefficient of static friction times mg cosine theta plus mg sine theta, that equals 0. Okay, now I need to solve this equation for theta. Okay, how am I going to do that? Well, first I'm going to move this negative term to the other side. So we have mg sine theta equals our coefficient of static friction, mg cosine theta. We've got an mg on both sides of the equation here, so I can divide both sides by mg. If I divide both sides by mg, those terms cancel. Okay, so then I have sine theta is equal to our coefficient of static friction, cosine theta. And we're looking to solve for theta. I want to get all the terms with theta on one side. So I'm going to divide both sides by cosine theta. So then I have sine theta over cosine theta is equal to our coefficient of static friction. And if you remember from trigonometry, tangent of theta is equal to sine theta over cosine theta. So this is saying that the tangent of our angle theta is equal to the coefficient of static friction. Take the inverse tangent of both sides, and then we find that theta is equal to the inverse tangent of our coefficient of static friction. This is the maximum angle that we can get to before our object overcomes that coefficient of static friction and is going to start sliding down the ramp. Okay, so we'll just plug in the numbers. Inverse tangent of 0.35, that's going to be equal to 19.3 degrees. We can incline that plane to 19.3 degrees. Once we achieve 19.3 degrees, then any angle that we go beyond that, our block is going to start sliding down the plane.